In the previous section, we deployed an FPGA VI. By the end of this module, you will be able to transfer latest data between the host and FPGA using programmatic front panel communication. If you want to transfer latest data between the FPGA and the host VI, what you can use is you can use programmatic front panel communication. Okay? The way that we would do this, we would use the read-write control function, which is shown on this slide. So what you would do is, in your host VI, you would place the read-write control function in there, and then you can read from or write to controls and indicators that are on your top-level FPGA VI. So when you're using this method, just remember that you're only transferring the latest data, and you're not getting buffered data. We'll talk about how to get buffered data in a later module. Okay, so let's take a look at an example here. So the first thing I want you to look at is the bottom. So on the bottom, we see we have an FPGA VI. Notice that we have a sample period control, and we have a couple indicators for status, code, temperature, CJC, and auto 0. Now let's take a look at how we would program the host VI to be able to transfer values back and forth. So first, what we're going to do is we're going to use an open FPGA VI reference, and notice there's an icon on there, and that's the icon of our FPGA VI. What I've already done is you've right-clicked it, and you've configured this function, and you've associated it with that particular FPGA VI. Okay, so notice out of this function, we pass a green wire, and that green wire is a reference to that FPGA VI. So if we look at the next one, read-write control, what we're going to do is we're going to wire that reference into this function, and once that wire has been connected there, then the read-write control will be able to know what controls and indicators are on that top-level FPGA VI. So notice that we can resize this function, and we can see temperature, sample period, CJC, auto 0, and status. So those correspond to what you saw on the front panel of that top-level FPGA VI. Okay, and so at this point, notice we were able to update the sample period just by wiring in some values, and we were also able to read the current values of that FPGA VI, temperature, CJC, auto 0, and status just by wiring it out of this function. Okay, so in this case, what we've done is we've read some of these values. We're putting it through a conversion VI to get our temperature, and we're just going to keep doing this over and over again. So remember that write-read control, or the read-write control function, is actually only doing latest values. At the end, we're closing our FPGA VI reference, and we're handling any errors on our host. So what are some use cases for transferring latest data using this method? So one, you might want to send configuration parameters or data from the host to the FPGA. So for example, maybe on your host, you want to let some user interface allow the user to set the PID gains and things like that. Well, you can set those configuration parameters on your host and then send them to your FPGA. You only need to know the latest data for that. And also you can use it to report status from the FPGA to the host. So maybe one example of latest data from the FPGA to the host that you might want to know is the overflow status. So if you're acquiring data on your FPGA and it overflowed, you might want to know that, and you can report that back up to the host using programmatic front panel communication. Also, you might want to send commands between the host and the FPGA. So for example, you might have a spot on your host VI where you're telling the FPGA, go ahead and start the control algorithm. Also, you might want to transfer latest data between the host and FPGA in general. So maybe you only care about what the current set point is. So in that case, we can use this method to have the host tell the FPGA what the current set point is and update it. And then lastly, on your host VI, you can also use it to create a test bench for your FPGA VI and get latest values down there by using the read-write control function. So another FPGA interface function you have available on your host is the invoke method. So this is going to invoke any method or action from the host VI. So some of the methods that are supported, you'll see there you can run your FPGA VI using a method, you can abort it, you can get FPGA VI execution mode, you can reset it, and we'll talk about a couple of these other ones like the IRQ and DMA FIFOs later on in this lesson. So these are just some methods or some FPGA methods you can invoke from your host VI. Your target also may support additional target-specific methods, more than the ones that are listed here. On this slide, we see a picture of the close FPGA VI reference function. So you want to put this function at the end of your host VI typically. And by default, what it'll do is it'll stop and reset the FPGA. So for example, it'll stop the execution of the FPGA, and resetting it this does things like clearing the FIFOs and things like that. So the default, if you look at that third bullet, the default selection on that is close and reset if last reference. What that'll do is it'll go ahead and close the reference. It'll stop the FPGA VI if there are no other open references to the FPGA VI, and it'll reset it. If you right-click it, you can also change the option. So if you look at that second bullet, you can right-click and select just close instead. And what that'll do is it'll close the reference to the FPGA VI, but it won't reset it. So what you can do is you can use a free label on your block diagram to kind of notate to the user which one of these you're using, whether it's close or if it's close and reset if last reference. So here let's make a couple of notes about these FPGA interface functions. So remember the FPGA interface functions on your host VI control and communicate with the FPGA VI. We saw the open FPGA interface VI, we saw the read and write so we can get things there, there's methods, and we talked about the close function as well. So second bullet, expose only necessary controls and indicators on the FPGA VI. So remember on that top level FPGA VI, the purpose of putting a control or indicator there should be because you want some extra logic on your FPGA to be implemented so that on your host you can actually update the latest values of those FPGA controls and indicators. So that third bullet, you can use a host VI to write values to your FPGA VI. So previously, when we were developing our FPGA VI and we're just trying to debug things and make sure things are working, you opened up the front panel of the FPGA VI, remember? And we just did some interactive execution or interactive front panel communication to get things tested. But in your final application, you don't want to do that. In your final application, when things are all wrapped up, you want to make sure that you create a host VI that will actually handle the communication to your FPGA VI. So at this point, it would be good to do exercise 11.1, Windows host integration, and in this exercise, you'll get some experience using the FPGA interface functions. So for now, I'm going to go ahead and demo this. What we're going to do is we're going to have an FPGA VI, and then we want to create a user interface for it on the Windows host system. So we're going to create a Windows host VI that communicates with our FPGA VI. Okay, let's take a look at exercise 11.1. So here I've opened the solution, and let's kind of go through it. Okay, so the first thing I want to open up is the FPGA VI, which is right here. So let's open this up. Notice that we've got some controls and indicators here. So we have a threshold control, a stop FPGA control, an indicator here, and an indicator here. So with these controls and indicators, because they're on our top level FPGA VI, that's going to allow a host VI to actually access the values here and write and read from them. Okay, so let's look at the block diagram real quick. So notice that the host will be able to update the latest value of our threshold. Okay, and we're reading from our analog input. So we're reading some value from our analog input. Notice that it's a binary value represented by I16. We are comparing that value, the IO value, to a threshold. And then based on that, if the threshold has been exceeded, we're going to write to our digital output line. And we're also going to write to an indicator, threshold exceeded. Because it's an indicator, I can actually access that from my host VI. Also from my host VI, I'm going to be able to access this stop FPGA control. And what we can do is, that means we can stop this FPGA loop gracefully from our host as well. Okay? So just remember the controls and indicators that we have up here, and we'll see how we can access them from our host. So let's go and open up the Windows host. Okay, so notice the Windows host is under my computer. I'm going to open that up, and my Windows host here is going to have a monitoring loop period, threshold, threshold exceeded, and the AI. So notice that these are in volts, and we'll take a look at the code behind this. So now we're on our host VI that's running on Windows. So the first thing we want to do is in the host VI, we want to actually open a reference to our FPGA VI. Okay, so let's right-click this and look at the configuration. So configure open FPGA VI reference. So in this exercise, what you would have done is you would have said, okay, well, I want to open a FPGA reference to this particular FPGA VI. Okay, so if I click this button, notice that when you select the VI, it's going to allow you to go through a project and then navigate to an FPGA VI. Okay, so in this case, I've navigated to that threshold FPGA VI that we looked at earlier. So I'm going to click OK. Now we've opened it and we've made the FPGA VI start running. Oh, let me show that real quick too. So notice by default it says run the FPGA VI. So in this case, not only is it going to open up the FPGA VI, by default it's also going to start running it too. So now the FPGA VI is running on our FPGA, and we're passing this reference here. So once I pass this reference into a read-write control, that read and write control is going to allow me to select controls and indicators that are on that top-level FPGA VI. So notice if I select this, this is being filled up with the names of the controls and indicators on my top-level FPGA VI. Okay. Notice that I can also expand it to get more. In this case, I don't really need to do anything with the stop FPGA control quite yet, so I'm going to resize it and not look at that one. Okay, so now let's take a look at what this host VI is doing. First of all, it's trying to monitor some of these values, and over here, this is just a wait until next millisecond multiple, so we can kind of control the loop rate of our host VI loop. And then over here, we're getting the threshold. So we want to set the threshold on our user interface in volts, right? It makes a little bit more sense for our users to put in 5 volts rather than the binary number that's associated with it, or the binary value that's associated with it. So what we're going to do is we're going to do some scaling, okay? So based on this formula, what we can do is, so this formula is coming from the nominal voltage range. So in this case, we have a nominal voltage range of, let's see, over here, it's going to be plus or minus 10 volts, okay? And we know that our AI channel is 16-bit resolution, which means it has 2 to the 16th different values, okay? So if we know that information, we can come down here and we can figure out what the binary value, the I16 value, that is associated with a particular voltage. So we're taking that voltage, we're doing some of that calculation here, and we're making it into an I16, and we're sending that to the threshold right here. Okay? And then on the output, when we're actually reading what the current analog input value is, we're going to convert that I16 to double precision floating point, and then we're going to scale that as well. So we're going to go ahead and divide it and go through here, and now on the user interface on our host VI, we get the analog input in engineering units, namely volts. Okay? So in this case, one reason why we're doing this conversion on our host is one, it's easy to do here. Also, this is using double precision floating point. So if you have an algorithm that's using double precision floating point, the FPGA VI does not support that. The FPGA VI does, however, support a single precision floating point. So here we've done some scaling on our host, and then when we hit the stop button on our host, we're going to exit this while loop, and when we stop that, we're going to send a stop to our FPGA control, which will gracefully stop that while loop there, and then we're also going to close the FPGA VI reference. Okay? And the last thing I just wanted to show real quick is if you've already set this open FPGA VI reference for a particular FPGA VI, if you double click this, it'll automatically open up the FPGA VI. So if I double click this, it automatically opens up the FPGA VI that's associated with it. Okay, let's do the discussion questions. So will the same scaling calculations that we used in the host VI work for I/O channels that have different resolution and a different voltage range? So if you remember from our host VI, the calculations were actually based on a specific resolution and voltage range. So for example, the calculations that we had were based on a 16-bit resolution and also a plus or minus voltage range. So once that changes, then the scaling calculations have to be adjusted as well. So the answer is no. The same scaling calculations won't work for something with a different resolution and voltage range. What functionality can a Windows host VI accomplish that an FPGA VI could not? So let's think about this. Well, the FPGA VI, it doesn't have a user interface, right? It's just being deployed to the FPGA chip. So one, the Windows host VI can provide a user interface for users to use and interact with the FPGA VI. Also, Windows, you can save files, right? So if you need to save log files, you can do that on Windows as well, but the FPGA could not. Also, any Windows-specific technology, maybe like databases and things like that, you can get a bunch of enterprise functionality by using a Windows host VI that FPGA could not do.